Hello and welcome. This is a video on drag. I'm going to include an example in the homework, Chapter 6 homework. It's problem 6.65. And I'm doing this because the classes had in-person today and there were different sections and different experiences. So I want to make sure to give something kind of coherent for everyone to access on the YouTube playlist. So before we get started on the homework problem, I want to just give an overview of the drag force. Now, the drag force, much like the friction force, well, it's certainly opposite the motion, but it's very complicated. If you look in the textbook about what friction is the result of these sort of microscopic bonds between two surfaces that are in contact with one another, and when they're sliding past one another, these microscopic bonds are breaking. And there's next to no way to be able to model that process. So the best thing we can do is create a model, say that the force is constant. And it's the same thing with the drag force. I mean, the drag force, you've got different, let's say you have a particle moving, I don't know, to the right or something, and the drag force, say if it's moving to the right, it's moving in a bunch of molecules, whatever the fluid is, whether it's air, whether it's water, and these molecules themselves have random motion. So we're in a sense pushing the molecules out of the way, and then the molecules in turn, by Newton's third law, push back on us. And that also, it's far too complicated to handle because the drag force depends on how many particles you're hitting, how fast they're moving, in what direction they're moving, the orientation of each of the particles to the object, and so it's very complicated. So the friction force and the drag force are two examples of forces for which we have to have a model. And so in general, we see that the drag force is a function of velocity. Okay, so technically it's a vector F that's a function of vector velocity V. In general, that's what it is. And we can simplify that using the result of Taylor's theorem, because Taylor's theorem states that any complicated function, whether it's a sine or cosine or exponential or some inverse hyperbolic arcsecant, they can always be modeled or approximated in a certain degree by the polynomial functions. Now this one's a little bit more difficult because it's a vector, but any function that you learn in calculus can be modeled as polynomials. And so for drag, we typically use the linear and the quadratic approximations. So let's do the linear one. And this linear drag force will be the one for which motivates the end of chapter problem that I'm going to be going over, 6.65. Okay, so the linear drag force is, I'm going to do F sub D. It's going to be, we're going to say it's minus B times V. So it just depends linearly on this velocity. So if you're traveling twice as fast, the drag force is twice as much. If you're traveling 3 times as fast, the drag force is pushing back 3 times the force. B is called a drag constant. And what are its units? Well, if the units of force is newtons, then the units of, units of velocity are obviously meters per second. Then what would be the units of the drag constant? That would, looking at it, the best way to do it is to just, more or less solve, in a sense, for the thing in the parentheses. So dividing by, or multiplying by seconds per meter, you get that the drag constant is Newton seconds per meter. Sometimes we call that kilograms per second. That's also a standard way to view the drag constant. Now, for a sphere, okay, we're going to simplify matters and just only consider the object that has a shape of a sphere. Because this drag, what does this drag constant depend on? It depends on several things, not only of the fluid, but also of the object. And so the simplest case is a spherical object of radius r moving in a static fluid with velocity v. And the fluid's not moving. If the fluid was moving, then it would be the same thing, but the drag force would be like almost a pushing force. You know, that's how spiders and little bugs float on air currents, and how we'll see in a minute, you know, some microorganisms can navigate through fluids in the cell or in like water or human body or something like a lake or something. So for our purposes, this drag constant B is equal to 6 pi eta times r. Again, this is only for a spherical object. So we'll make a note of that. A spherical object. So obviously r is the radius, and 6 pi you can calculate. That's 18.84. But what's eta? Eta is called that's Greek letter eta. That's called the viscosity of the material, of the fluid rather, not the object. It's the viscosity of the fluid, and that's a quantity that for which tremendous attention is devoted to it in fluid dynamics and in aerospace and design of mechanical systems that move through the water or move in air. Anytime you're having anytime you're having an object move through a fluid, that fluid is characterized by viscosity. Now, what are the units of viscosity? Well, same thing for units of B. If we plug in the units of B here, newtons per second, newton seconds per meter, you know, 6 pi doesn't have any units. R is meters, and so you can almost divide that meters again on the right-hand side to get a squared, and so we get that the units of viscosity are newton seconds per square meter. It's not a unit, or it's not a quantity that we're going to devote much time to, but it's certainly one that folks in, for instance, like mechanical engineering or even aerospace might use in their calculations of fluid flow or in their calculations of objects moving through fluids. For water, the homework problem, which is 6.65, gives us the expression, the viscosity of water, which all of these quantities are usually temperature dependent. You can imagine if you have like thick syrupy stuff, I mean, you can imagine that viscosity kind of decreases as you heat it up. Viscosity of a lot of liquids kind of decreases as you cool it, but before it solidifies. And so all these quantities are temperature dependent. And at room temperature, roughly 20 Celsius, our viscosity is 0.01 or 0.0010 Newton seconds per square meter. Okay, and so in the problem, we've got a bacteria or a E. coli or a bacterium or a paramecium, and we're asked what is the propulsion force needed for a bacteria to swim in water at a steady speed. Right, and so that speed will change depending on the force will depend on the speed, and the speed in this problem is given. So for the paramecium, we're given that the paramecium, first of all, what is it look like? Well, that's not a big deal. What matters is the modeling it as a sphere, and I think they say that it's about 100 micrometers in size. Of course, it's probably not exactly shaped like a sphere. There's nothing on the microscopic level that is. There's all these spikes and all this stuff, like dust and pollen and everything shaped weird in that scale, but we model it as a sphere to keep things easy. And so that means the radius then, if it's 100 micrometers wide, micro is 10 to the negative 6, and so 100 10 to the negative 6 divided by 2 will give you the radius that we'll use to calculate, which is 50 micrometers or 5.0 times 10 to the negative 5 meters. Okay, so we got viscosity and we got our radius, and if we do our speed, the book has this object moving at a speed of 1.5 millimeters per second. So we'll tack on a 10 to the negative 3 meters per second there. Okay, so in this example, what's the force that the bacteria needs to exert, through the little flagella or whatever it does in order to maintain at that constant speed? And to put it into perspective, you have a particle that's about 0.1 millimeters big, moving at 15 millimeters per second, or moving at 1.5 millimeters per second. So that would be like a person moving at kind of a heavy pace, like a heavy jog, maybe an all-out sprint. So pretty fast to scale. So let's do this calculation. Let's do an example of it. The numerics will help. Going to clear the drawing and start over. Okay, so obviously if this little circle thing is moving, to the right in the static water, then the free body diagram is very simple. It's just the drag force backwards, F sub D backwards, and this sort of propulsion force forward, and they cancel. So we have F net equals 0. So we're trying to find this propulsion force, and obviously it's equal to the drag force. And so we got propulsion. What mastering physics will ask for is propulsion force, but that equals this linear drag force. So that's going to be B, the magnitude. So it's 6 pi eta times radius times the speed. And it's helpful to plug in some of these numbers. It's good practice with lots of scientific notation. We got 6 pi. The viscosity is 1.0 times 10 to the negative 3 Newton seconds per square meter. That's an interesting unit, Newton seconds per square meter, because newtons per second has units for momentum. It's kind of like a unit that kind of sounds like momentum spread out over an area. And certainly that's one interpretation when you get to fluid flow. Radius, 5.0 times 10 to the negative 5 meters. And then the speed of 1.5 times 10 to the negative 3 meters per second. All right. So we can calculate that. It's not hard to calculate. You could even just put it in a pocket calculator, 6 pi times 5 times 1.5. And then how are the powers of 10 going to resolve themselves? We've got a 10 to the negative 3 for viscosity. We got 10 to the negative 5 for radius. And we got 10 to the negative 3 for velocity. So that's 10 to the negative 11th. And so we're left with an answer of going kind of up here. The propulsion force equals 6 pi times 7.5. That's 5 times 1.5 times 10 to the negative 11th newtons. And if you work that out, I mean, the part of the problem is finishing this calculation, but 6 pi is 6.28 times 2. So that's 18.84 times 7.5, 18.84 times 7.5, that is about 150. So you should get about, I wouldn't enter this in, I would double check it, probably about 1.5 times 10 to the negative 9 newtons. So that's the expected value to get for the propulsion force of this little paramecium moving at that small speed. That's the first part of the problem. And you have to do this for an E. coli bacterium. In the second part, they say, well, what's the acceleration going to be if there was no drag? Because the bacteria have to apply this force to maintain a constant velocity. But if there was no drag, right, then, so part B, if there's no drag, find A. then it's just that force you just found, the propulsion force over the mass of the object. So A equals that propulsion force. Now, what's the mass of the bacterium? We don't know, but we know the size of it, and we're told to assume that it's the density of water. So if you use the simple equation of mass equals density times volume, then density is 1,000 for water, kg per cubic m. The volume of a sphere is 4/3 pi radius cubed. And so even if you wanted to use the given values instead of the propulsion force, just want to make it use variables, you can even do some substitutions to get an answer. So at the numerator, it's going to be 6 pi eta RV divided by rho 4/3 pi r cubed. And so you see the r's are going to cancel, the pi's are going to cancel. 6 and 4/3 will resolve themselves in some way to 9/2, I think. And so we end up with 9/2. We usually write it like this: the fraction is out, the fraction of the number is out in front, and then there's another fraction with all the variables. So the other variables are going to be eta v over rho r squared, density of the water times radius of the thing squared. So that's probably the simplest way to figure that out. And the point of this question is to make the problem look like, kind of see what those accelerations would be. You might surprise yourself. I mean, we got not even counting the 9/2, which is kind of like 5. How big is this? Viscosity times speed, that's the speed, not a volume, is about, well, just really quickly, I'm not going to calculate it out because that's the point of the problem, but viscosity times speed is about, for this case, about 1.5 times 10 to the negative 6. And those units, get stickier from there. I mean, it's like, I don't even know what that unit is. But on the bottom here, you got like 10 to the 3, 10 to the 3 from the density of water. And then the radius squared is 5, let's see, it'd be 5 times 10 to the negative 5 squared. So we have what looks like a 10 to the 3, 10 to the negative 10. And so it looks to me like you're going to have an acceleration, if I would guess, about a really big one, about 10 to the 4 meters per second squared. So these are very short, very big bursts of acceleration. Because you have on the bottom, so on the top you have 10 to the negative 6. On the bottom you have 10 to the negative 10. 3. No, sorry. Let's see. You have a 3 and then a 10, so it's negative 7. So actually it's not 4. It's more like 10 to the, maybe 10 to the 2. So it's a little bit smaller than that. So that's the point of this problem, and it's a good application of the linear drag force. I would keep this idea of linear drag force in the back of your head as we're going to be using it in later chapters. And so the next topic is quadratic drag. Where we model the drag force as depending on the square of the velocity, not linear. And this is the one that's in the drag section. We say at F drag, the magnitude of it is equal to 1/2 rho CAV squared. What are all these terms? Well, the velocity squared is obviously the speed squared. A is the cross-sectional area. So a few simple geometries that we consider are a sphere. So the sphere, it's just the cross-sectional area of the sphere is the same no matter what. It's just a circle. Cylinder. Well, the cross-sectional area of the cylinder will depend on the direction in which it's moving, its orientation. So if the V is down, if it's moving towards one of its sides, then the area is a circle. And so it's like looking down at the top of a soda can or pop can. If it is moving down that way, then the area is a rectangle. Like that. So the cross-sectional area will change depending on not only the object, but depending on the shape of the object as well, and in the direction of motion, orientation of the object. Typically, objects tend to equilibrate themselves when they're moving in fluids such that their center of gravity is the lowest, but that's not really relevant to a conversation. So that's cross-sectional area. Rho is the density of the fluid. So for air, the quoted values typically 1.3 times, 1.3 kilograms per cubic meter. And that the density for gases, as we'll see in thermodynamics, is certainly dependent on the pressure and the temperature and the number density. It depends on all these other thermodynamic quantities, but this is the density of air at room temperature at standard, atmospheric pressure. So that leaves us with this capital C. What's this capital C right here? We have a drag constant in the linear drag. Capital C is called the drag coefficient. And that's a number that's going to range between 0 and 1. And it's going to depend on the actual shape of the object. So if you imagine like a little toy car, like a toy Corvette, and then the big Corvette at the same location, right, right next to it, their drag coefficients would be the same because it only depends on the shape of the object. Your textbook will have different values for these drag coefficients for these shapes. And, it varies. I mean, mid-sized sedans will have like a drag coefficient of about 0.2 or 0.25. Compact cars, because they are more aerodynamically designed, will have a smaller one like 0.15. Trucks and SUVs, for which payload is more of a important feature, will have bigger coefficients like 0.4, and performance cars will actually have ones that are even higher, like 0.45 or sometimes even 0.5, right? Performance cars want a big drag coefficient to get a big drag force so that the air can push down more on more or less an angled surface, right? Which will increase the normal force and then increase friction and torque that the wheels provide to the street. That's a simple estimate of the drag coefficients. And so most problems with the drag force like this will just have you look through and plug in all these values. You might have to do a conversion or two, make sure you got the right density, look up the drag coefficient in the book. You don't have to look it up on like a reference website, but the thing that I wanted to really focus on before I end this video is reasoning about drag in general. And what I want to do is I want to start out with a small object at the very top that is released from rest. Its initial velocity is 0, and it's released from rest very high up in the air. To give you a sense of scale, a penny can reach terminal velocity if it's dropped from the height of a skyscraper. So a couple thousand feet up in the air, about 500-600 meters is enough for a small penny-shaped object to reach its terminal speed. And so let's describe qualitatively how that does it. So when we release it from rest initially, there's only gravity, right? So we got mg down, which means we have an acceleration equal to g. So what's that acceleration going to do? Well, it's going to do what all accelerations do. It causes the object to change its motion. In particular, it'll make this one speed up. So the falling ball will now have a modest downward velocity. Well, what's the presence now? Once it's moving in air, okay, because that's an important thing, is that we're not ignoring air resistance. We're in air. We're in a fluid. The velocity now will cause the ball to feel a drag force, and so that drag force, relatively small, but still pointing upward. And here's the critical idea. This is the key part of it. As the particle speeds up, that increases the drag force. Well, the drag force will lower the acceleration. So now we have an acceleration that's smaller than g. Lots of vectors here. But the smaller acceleration, it's still pointing in the same direction as v, so it'll cause the ball to speed up even more. Okay, it's going to cause it to speed up any more, and so that will make the drag force increase even more, which will lower the acceleration even more. So now the acceleration will get even smaller. It'll be much, much less than g, but it'll still speed up. And so you can get in this pattern of the acceleration causing the ball to speed up, but if it speeds up, then drag increases, that lowers the acceleration, but that still makes the ball go even faster, but that increases the drag, which lowers the acceleration, which speeds up the ball, which lowers or increases the drag, which lowers the acceleration. And you get to the point where the drag force has increased to the point where acceleration is zero. You don't really measure any difference in velocity from instant to instant. And that is when we would say that the object is in terminal velocity. For quadratic drag, once those are equal, you're going to have 1/2 rho c a v squared equal to mg in air. And so you can solve for v and get an expression for the terminal velocity. Being 2mg over rho ca square rooted. That ends up being an expression for terminal velocity that you find in the textbook. And so that might be interesting. One application that's kind of interesting that's worth looking at in this terminal velocity equation is looking at the terminal speed of hailstones. In severe weather week, you of course start hearing about pea-size hail or nickel-size hail or dime-size hail or quarter, or it's even worse, softball or baseball-size hail. I mean, really bad hail, really severe storm. Interestingly enough, if you model the hailstone, it's just falling in an air that's not moving. In the numerator here, you have the mass of the hailstone. The mass of the hailstone is, the density of ice times the volume of the thing. So there's 4/3 pi radius of the hailstone cubed. That cubed is important for what I'm going to say next. Okay. Well, the numerator has like a radius cubed in it. The denominator, it's got the drag thing that stays the same as long as hailstone stays spherical, and then rho is the density of air, not water, so the densities don't cancel. But the cross-sectional area is like pi r squared. And so what you have here is that the bigger the hailstone, the bigger the radius, the faster the terminal velocity. And so we have a relation between the ratio of terminal speeds of two different sizes is proportional to the square of the ratio of the radii. these ratio type problems, I mean, put that in perspective, like a volleyball, I mean, a big ball and like a golf ball, right? Yeah, that's like a golf, if you think about it, like a, oh, maybe like a, how about like a baseball and a quarter? That's reasonable, like quarter size hail versus baseball size hail. But this says that the terminal velocity of the baseball size hail is moving twice as fast as the terminal velocity of the hailstone. So that should certainly frighten us as we gear up for for severe weather in the spring. Okay, and so overall big picture view about drag is that there's linear and quadratic drag. Quadratic drag is more helpful to find a quick way for the terminal velocity. Linear drag, in my opinion, is more important for other applications that we will see in later chapters. For instance, like a pendulum swinging, if you include drag, if you include like a quadratic drag, as this pendulum is moving, let's say that way, it's got a drag force that way, gravity that way. The calculation of the motion of this pendulum with drag is most accurate when using linear drag. And we'll see how we do that in some later chapters on oscillations. So yeah, this is just an overview of drag. I want to post this to the channel so everyone has a equal sort of discussion of this topic. So till then, thanks for your time, and we'll see you back here in the next video. Take care.